IT Network Plus course. Inverters. A power inverter is a type of power converter that specifically converts DC to AC. It produces no power and must be connected to a DC source. Power redundancy. While the facility itself needs redundant power circuits and backup generators, a system can still fail if the power supply in the device fails. Mission critical devices should be equipped with redundant power supplies which can mitigate this issue. Device placement. When locating equipment in a data center, server room or wiring closet, the placement of the equipment should take several issues into consideration. Airflow. Airflow around the equipment is crucially important to keep devices running. When hot air is not removed from the area and replaced with cooler air, the devices overheat and start doing things like rebooting unexpectedly. Even if the situation doesn't reach that point, the heat itself will shorten the life of costly equipment. One of the approaches that has been really successful is called hot aisle, cold aisles, as explained earlier in this chapter. Hot aisle, cold aisle design involves lining up racks in alternating rows with cold air intakes facing one way and hot air exhausts facing the other. The rows composed of rack fronts are called cold aisles. Typically, cold aisles face air conditioner output ducts. The rows the heated exhausts pour into are called hot aisles. They face air conditioner return ducts. Moreover, all of the racks and the equipment they hold should never be on the floor. They should be a raised floor to provide some protection against water. Cable trays. Masses of unruly cables can block airflow and act as a heat blanket on the equipment if the situation is bad enough. Cable trays are metal trays used to organize the cabling neatly and keep it away from the areas where it can cause heat buildup. Figure 2017. Some examples of cable tray components are shown. They are used to organize the cables and route them as needed. Rack systems. Rack systems are used to hold and arrange the servers, routers, switches, firewalls, and other rack-ready equipment. Rack devices are advertised in terms of use. U is the standard unit of measurement for designing the vertical unusable space or the height of racks. 1 U is the equivalent of 1.75 inches. For example, a rack designed as 20 U has 20 rack spaces for equipment and has 35 20 x 175 inches of vertical usable space. You should be familiar with the type of rack systems and components. Server rack rails. Server rack rails are used to hold servers in one type of racks described next. They are designed to hold the server while allowing the server to be slid out of the rack for maintenance. Two-post racks. A two-post rack is one in which only two posts run from the floor. These posts may reach to the ceiling or they may not. Freestanding. Several sizes of two-post racks are shown in figure 2018. Four-post racks. As you would expect, these racks have 4 rails and can be either floor or ceiling or freestanding. One is shown in figure 2019. Freestanding racks. A freestanding rack is one that does not reach the ceiling and stands on its own. A 4-post freestanding rack is shown in figure 20.20. Labeling. In a data center, server room or wiring closet, correct and updated labeling of ports, systems, circuits and patch panels can prevent a lot of confusion and mistakes when configuration changes are made, working with incorrect or incomplete, in some cases non-existent labeling is somewhat like trying to locate a place with an incorrect or incomplete map. In the next section, we'll touch on some of the items that should be correctly labelled. Port labeling. Ports on switches, patch panels and other systems should be properly labelled, and the wall outlets to which they should and the outlets to which the lead should match. You should arrive at an agreement as to the naming convention to use so that all technicians are operating from the same point of reference. They should also be updated in any case where changes are made that dictate an update. System labeling. Other systems that are installed in racks such as servers, firewall appliances, redundant power supplies should be labelled with IP addresses and DNS names that the devices possess. Circuit labeling. Circuits entering the facility should also be labelled. Label electrical receptacles, circuit breaker panels and power distribution units. Include circuit information, voltage and amperage, a type of electrical receptacle, and where in the data center the conduit terminates. Naming conventions. A naming system or convention guides and organizes labeling and assures consistency. No matter what name or numbering system you use, be consistent. Patch panel labeling. The key issue when labeling patch panels is to ensure that they are correct. Also, you need to make sure that the wall outlet they're connected to is the same. The American National Standards Institute Telecommunications Industry NSITIA 606 B1 Administration Standard for Telecommunications Infrastructure for Identical and Labeling, approved in April 2012, provides clear specifications for labeling and administration best practices across all electrical and network systems premise classes, including large data centers. Rack monitoring. Racks should contain monitoring devices that can be operated remotely. These devices can be used to monitor the following issues: temperature, humidity, physical security, open doors, smoke, water leaks, vibration. Rack security. Rack devices should be secured from theft. There are several locking systems that can be used to facilitate this. These locks are typically implemented in the doors on the front of a rack cabinet. Swing handle, wing knob locks with common key. Swing handle, wing knob locks with unique key. Swing handle with number and key lock. Electronic locks, radio frequency identification, RFID card locks. Change management procedures. Throughout this chapter, I've stressed that network operations need to occur in a controlled and managed fashion. For this to occur, an organization must have a formal change management process in place. The purpose of this process is to ensure that all changes are approved by the proper personnel and are implemented in a safe and logical manner. Let's take a look at the key items should be included in these procedures. Document reason for a change. Clearly, every change should be made for a reason before the change is even discussed. That reason should be documented during all stages of the approval process. Discussed later. This information should be clearly communicated and attached to the change under consideration. Change request. A change should start its life as a change request. This request will follow through various stages of the approval process and should include certain pieces of information that will guide those tasks with approving or denying it. Configuration procedures. The exact steps required to implement the change and the exact devices involved should be clearly detailed. Complete documentation should be produced and submitted with a formal report to the Change Management Board. Rollback changes. Changes always carry a risk before any changes are implemented. Plans for reversing the changes and recovering from any adverse effects from the change should be identified. Those making the changes should be completely briefed in these rollback procedures, and they should exhibit a clear understanding of them prior to implementing the changes. Potential impact. While unexpected adverse effects of a change can't always be anticipated, a good faith effort should be made to identify all possible systems that could be impacted by the change. One of the benefits of performing this exercise is that they can identify systems that need to be more closely monitored for their reaction to the change as the change is being implemented. Notification. When all systems and departments that may be impacted by the change are identified, system owners and department heads should be notified of all changes that could potentially affect them. One of the associated benefits of this is that it creates additional monitors for problems during the change process. Approval requests. Requests for changes should be fully vetted by a cross-section of users, IT, personnel, management and security experts. In many cases, it's wise to form a change control board to complete the following tasks. Assure that changes made were approved, tested, documented and implemented correctly. Meet periodically to discuss change status accounting reports. Maintain a responsibility for assuring that changes made do not jeopardize the soundness of the verification system. Maintenance window. A maintenance window is the amount of time a system will be down or unavailable during the implementation of changes. Before this window of time is specified, all affected systems should be examined with respect to their criticality in supporting mission critical operations. It may be that the time required to make the changes may exceed the allowable downtime a system can suffer during normal business hours, and the change may need to be implemented during the weekend or in the evening. Authorized downtime. Once the time required to make the change has been compared to the maximum allowable downtime a system can suffer and the optimum time for the change is identified, the authorized downtime can be specified. This amounts to a final decision on when the change will be made. Notification. When the change has been successfully completed and the sufficient amount of time has elapsed for issues to manifest themselves, all stakeholders should be notified and the change is completed. At that time, these stakeholders, those possibly affected by the change, continue to monitor the situation for any residual problems. Documentation. The job isn't complete until the paperwork is complete. In this case, the following should be updated to reflect the changed state of the network configuration, additions to network, physical location changes. Summary. In this chapter, I have talked a lot about the documentation aspects of network administration. I started off discussing physical diagrams and schematics and moved on to the logical form as well as configuration management documentation. You learned about the importance of these diagrams as well as the simple to complex forms that can take the tools used to create them, from pencil and paper to high-tech AutoCAD schematics. You also found out a great deal of creating performance baselines. After that, I delved deep into discussion of network policies and procedures and how regulations can affect how you manage your network. Next, you learned about network monitoring and optimization of how monitoring your network can help you find issues before they develop into major problems. You learned that server operating systems and intelligent network devices have built-in graphical monitoring tools to help you troubleshoot your network. We got into performance optimization and the many theories and strategies you can apply to optimize performance on your network. All of them deal with controlling the traffic in some way and include methods like QoS, traffic shaping, load balancing, high availability, and the use of caching servers. We discussed how Common Address Resolution Protocol CARP can be used to increase availability of gateways and firewalls. You also learned how important it is to ensure that you have plenty of bandwidth available for any applications that vitally need it, like critical service operations, voice, VoIP, and real-time multimedia streaming. Finally, we discussed cloud computing or virtualization. We looked at its benefits, including increased performance and fault tolerance, increased availability, and the ability to access cloud services from anywhere. You also learned about some of its major components, such as virtual servers, virtual switches, virtual desktops, and an example of software as a service, SaaS, virtual PBX. So this concludes on my training of the Comptia Network Plus course. I hope you really enjoyed it. So please give me a thumbs up and share if you like this video, and thank you.